Hello, everyone, and welcome to our joint AAPG P&ATS webinar event titled Well Abandonment with Creeping Formations. My name is Pierre-Edouard Vincent, and I serve with the SP, P&A, and Well Integrity Technical Sections. My fellow host, Susan Nash, with AAPG, and myself will be your hosts and moderators today. This event will last 60 minutes, roughly, but will not have a hard stop. We encourage you to ask questions throughout, which we will use to fuel the discussion. Most of you will be joining via LinkedIn, but if you're experiencing technical difficulties, you can also use the alternative YouTube link provided on the LinkedIn page, and I'll paste that in the chat box. This event will be recorded and available on demand on various platforms. Um, as an intro, before we start, I would like you to consider joining SPE and access the many benefits of being a member, and also join various technical sections like the one on P&A and Well Integrity, both available through SP Connect and LinkedIn. And of course, AAPG, Susan will tell you a few things about that. So Susan, if you have an update on activities at AAPG.
Oh, thank you. And it's really a pleasure and an honor to be here. I'm really happy to say that we have an ongoing webinar series at AAPG as well. And we have sort of had a little bit of crossover where we talked about orphan wells, abandoning wells, and well integrity. And also, I just want to encourage people to attend the OTC, which is coming up, and also Your Tech. Both are in Houston. So it'll give you a chance to learn a lot and then also to check out what is going on in Europe, in Asia Pacific, and in Latin America. So thank you.
Very good. For the P&ATS, I'm going to show you the QR code. If you want to consider joining our section, you can look it up. It's so you need to be an SP member to be on SP Connect, but if you want to join us on LinkedIn, you do not. And then before we go on and introduce our speaker for today, which Susan will do, I'll show you a little graphic, a poster for the next event we'll have. There'll be the second webinar discussing squeezing formations, and Eric Van Oort at UT Austin will be talking about his work there, and it should be quite an interesting topic as well. Now over to you, Susan, for introducing Fabio.
Thank you, Pierre-Edouard. So our speaker, Fabio, graduated in 2010 in aeronautical mechanical engineering from the Instituto Tecnológico de Aeronáutica, ITA, and earned a master's degree in civil engineering focused on geotechnics in 2024. From 2010 to 2013, he worked in an organization of the Brazilian Air Force responsible for the construction of aerodromes, air bases, and the Army's frontier battalions. In 2013, he joined Petrobras and specialized in petroleum engineering at Petrobras Corporate University. Fabio then worked as a company man for 1 year before joining the Petrobras Research Center at CENPES, where he coordinated R&D projects such as drilling geomechanics, well foundation design, as well as in the development of engineering software related to these disciplines. Since 2018, he's been working in the corporate subsea wells department at Petrobras, providing engineering guidelines and technical support. He's now acting as technical advisor for wellbore stability and well foundation design. I'm really looking forward to this. And I love the geological crossover too. Welcome,
Thank,
Fabio.
thank you very much, Susan, Peter.
The floor is yours.
Okay, so I'm gonna talk about well abandonment with creeping formations. So the first thing I would like to say is that this work was made by many colleagues here. I'm just the messenger. So we have it's a multidisciplinary work involving geologists, involving engineers, and many people here inside Petrobras. So we'll go through this agenda first. A little bit of a motivation for the work, a proposed methodology to evaluate salt as a barrier, and then after another methodology to evaluate shale, and then I'll go through a proposed workflow for qualification and verification of this type of formations acting as well barriers, and finally some potential future developments. So is the creeping formations a problem, really a problem, or a solution to our wells? So when we talk about drilling or running casings into a hole, this could be an issue. So, for example, we have a type of formation in the Brazilian coast, in a certain part here of the coast, that we need to drill the second section of the well with a dual rig, so we can perform the drilling, and shortly after the drilling we need to run the casing because the we have a plastic shale that creeps in the well, and if we do not go fast enough, the well closes and we cannot run the casing. So this could be really an issue. And also we could have during drilling operations stuck pipe problems or things like that. So it could be really a problem when we talk about drilling or the construction of the well. But when we talk about well abandonment, this really could be an advantage. So it would be a silver lining for the methodology. So we could use the shale as a barrier. We could count on its closing around the casing, and it could form a permanent barrier for fluid flow. We can test this, and we can uh, save some money because we wouldn't need to put, for example, cement behind the casing for the well abandonment. So this the creeping formations can be a problem during construction, but for when we talk about well abandonment, they can be a solution actually. So starting with the salt, the evaluation of salt as a barrier first, we'll go talking about a little bit of the behavior of salt under stress. So we have here, I'm showing two specimens of halite. These are real specimens of tests that we could perform in the lab. So that we can assume that the both halides have the same mechanical properties. They look the same. They have the same behavior under stress in general. So when we performed the tests, we did it in the same temperature conditions, so 86 degrees Celsius here. But we executed the tests in different deviatoric stress. So the test was a triaxial test, and we can see in the charts here very different behaviors. So in the first case, the top chart here, we use 20 MPa and 86 degrees Celsius, and we can see that the salt uh, went through all the stages that we understand for the creeping behavior. So it went through to the primary creep, secondary creep, and tertiary creep. And this, in the second case here, in the chart below, we used 8 MPa, so almost half the deviatoric stress from the first case, and the same temperature. And we see that the similar specimen, it went only to the second stage. It went through the primary creep and then secondary creep, but it didn't reach the tertiary creep. And we are talking about a very different time stamp here. So the first one was a 600-hour test, and the second one is a 2,600 hours test. So we can see that for 600, it was still in the secondary creep state here. And when we see the how the specimens finished the test, in the first case where it reached the tertiary creep, the specimen was all destructed. And in the second case, we almost cannot see a deformation here in the specimen. So it it means that when we are thinking about our well, depending on the conditions of the well, I mean the mud density that we use for to drill the salt section, the temperature of the salt in the field, and also the lithology that is behind the casing, we can have very different behaviors. And sometimes we can expect the salt to creep in and form the barrier, and sometimes not. And in this case, if we could reach the tertiary creep here, we could have many problems with the caliper of the well, because the rock could release some bigger pieces inside the well, and we could have many problems around that. So when we talk about a well, we should be really thinking about controlling the deviatoric stress that we are imposing to the rock when we drill the salt section. Uh, to model the behavior of salt, we use the double mechanism model. It is known as double mechanism because as you can see here in the chart, it has two different behaviors here. Uh, we have two different inclinations here. So we have a reference deviatoric stress that in this case would be 10 MPa. So when we reach this deviatoric stress, the behavior of the salt changes. So the creep rate increases. This is why the law is called the double mechanism model, and this would be the equation that represents the creep rate of the salt. These parameters should be uh, should be defined with through the tests that we do perform in the lab. So all the operators should have salt samples, perform lab tests, and acquire this information so they can have a more reliable model for this double mechanism. We have here the names and the units that we use in in these parameters, but mainly it depends on the deviatoric stress. It depends on the of the relation between the deviatoric stress that we are applying in our well and the and this reference deviatoric stress here. It depends on temperature, obviously, and uh, and also it's in some properties like activation energy that are different for each type of salt. So this is what this is the model that's widely used in finite element models to represent the behavior of salt. Now I'm gonna show you an example of application of that double creep model. So here we can see an example of a simulation that was applied to a real well, but we assumed that in the top of cement, the top of cement of the of the salt section, we have a 30-meter halite, and in the second case, we have 30 meters of carnallite. The carnallite is known to have a higher creep rate compared to halite, and the tachyhydrite has a even higher than carnallite. So, depending on the lithology, the velocity that the salt would creep in changes very much. So in this first on the left hand side here, we can see the chart for halite. We can see that in 35 years, that would be probably the life cycle of a well. this halite would not reach the casing. So the dashed line here shows the expected closure from the nominal diameter of the open hole to the nominal outer diameter of the casing. So it wouldn't probably in this case this halite, this 30-meter layer of halite would not form a barrier. So when we see carnallite in the same conditions of temperature, the same depth, in the same overburden, we can see that the carnallite would form, would touch the casing in a period of 3 years. So it's really very fast and has a very high closure distance here compared to the halite. So using the same assumptions, we created a metric, kind of a ratio to compare if to see if the salt formation has a potential of creeping in and forming the barrier. So we are comparing the time of a certain intervention of the well. I mean, from well construction to the first heavy workover that we would have in the well. This would be the intervention time, and for the contact would be the time that we expect the salt to touch the casing outer diameter. So this ratio could bring us maybe a decision making parameter, so we can decide if we can run a log to see if the salt is really touching the casing. So we did this for 6 wells where we have similar intervention times here, like 6 years, 4, 3, and we modeled the salt, and we saw how much time would the salt would be touching the outer diameter of the casing, and the parameter is shown here. So we could define like a range, so we can have a high probability of the well barrier being formed in the salt section, maybe and no. So this is something that an operator could do in order to decide running a bond log to see if the expected behavior of salt really happened in the field. So that brings a methodology for salt. Now we're going through a methodology for evaluation of shale as a barrier. So it all started here in Petrobras with some cases of wells that we ran bond logs, and in those bond logs, we had an expectation for the top of cement, and we saw in the bond logs that above the top of cement, the bond logs were showing a good cement, or a good response in the bond log. So we assumed that this good response obviously was not cement; it was the shale that crept in and was touching the casing, and we saw the response of these formations in the bond logs. We asked the specialist, the bond log specialist here in Petrobras, to have a kind of a ranking. So we asked them for like 3 different levels. So no bonding, uncertain, and bonded. And we saw that the interval of interest would be this highlighted here, that we have shales, and the specialists classified the interest, the interval of interest as we asked. So we can see here the in the left in the right hand side here, different intervals that we called interval B, C, and D, where we see different responses on the bond log. And we can see here that the in the interval B that this would be the top of cement. So the shale that's free to creep in would be in the intervals C and D here. And we can see that the response from interval C was good. We have a lot of greens here. And in interval D, we have uncertain or no bonding. So we understood that the shale that's in this interval C would be the one that would be seeking to use as a potential barrier for the well. So having a zoom here in the seismic profile, the geologists that work with us, they mapped those intervals from A to D, and the interval C would be the one that we are interested in. Um, uh, One thing that we could do to map the lateral continuity of these formations is uh, use the formation thickness map. That this would be an isopec map where we can see the thickness of specifically the interval D around the field. So we have a thickness varying from 0 to 325 meters, and the map here is showing that we have the shale present in the whole field, but when we see the center of the field, we have higher, greater thickness of this type of shale. So this would bring us the information that the wells that are placed here in the center part of the field would be the ones with the higher potential of having the shale as a natural barrier for the fluid flow. Another technique of mapping the continuity, and also if this formation is prone to form the barrier, would be using the seismic attributes. So we also had the help of geophysicists in this work, and they proposed this attribute would be sum of negative amplitude, and the target shales would be shown here in red. So the red is the shales that have most potential of forming the natural barrier. Uh, okay, so the map it's showing that we have a good lateral continuity of the shale, and it and including this shale goes beyond the limits of the field that we were studying. So we could use this to map the shale in other like in other neighbor fields that we would have. So this brings a very good potential. We could increase the radius here of the seismic, and we could use the same seismic attribute to map this around many fields here that are close to this one, and that have the presence of the same shale as interval C. Another important issue that we should be mapping for these shales would be the geochemical properties. So it's known from literature that the clay content and the total organic carbon are known to affect the creep behavior of shales. So we took some samples of cuttings in the wells that we were studying, and we sent it to the lab, to our lab in to our Petrobras R&D center, and they analyzed the clay content. We performed X-ray diffraction tests. We performed geochemical tests. Like here, we can see the organic, the total organic carbon, uh, and we could map what geochemical properties we were looking for when we want this shale to behave with the creep the creep that we need to form the barrier. So using this type of information, we could analyze the cuttings in other fields, and if the shales from these other cuttings would have the same geochemical properties, they would have the potential to form to creep and to form a barrier, and we could use this information to decide like performing a bond log in an opportunity of a workover. This would be something that we were talking about, and we could use the same methodology, seismic, to map those shales that we are interested in. So summarizing here the information to identify the creeping shale, uh, I'm 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 naming this part of the process here the pre-qualification. So in order to the shale to form the barrier, it should be reaching those properties that we are mapping in the ones that we know that form the barrier. So in order to evaluate this potential, one thing that we could do first is to see intervals in the bond logs to identify that the shale creeped in and touched the casing. We can use the seismic seismic attributes. We can map the layers, and we can evaluate the lateral continuity of those shales. Use seismic attributes to map properties, not only the continuity, but to map also the properties of the shale that brings us to the behavior that we want. We should be doing a mineralogy characterization that could be done with cuttings, or it could be done with core samples too, lateral coring and everything. We should be performing mechanical properties characterization. In this case here, we couldn't do that because we only took cutting sample. But if we really believe that this shale could have the behavior that we want, we should be taking some core samples and performing a mechanical properties characterization in the lab. So like me triaxial tests and creep tests also in the shale, so we could generate a model like that double creep that we used in salt. We should be doing that for shale too. So in this case here that I'm showing you, we still didn't have those lab tests, so we still don't have the model to represent the creeping shales. I mean, in the particular case of the shales that we have here in Brazilian coasts. And at last, we could generate also correlation of properties with well logs. This is a very a very good advantage because we wouldn't need, if we have good correlations, we wouldn't need to have corings, and we could save some money. I mean, acquiring samples in the wells. We could use the correlations and also the cuttings that would be cheaper than doing a core to evaluate the behavior of shales in different fields that we want to qualify that formation as a barrier. So a proposed workflow here for the qualification. We have an overview here of the process that we start with the pre-qualification. That would be in the case of shales, evaluating all those parameters that I showed before. We can do that before performing any bond logs or any pressure tests in wells. And also for salt, we could use the double creep model to simulate the conditions of the wells that we have to see if the salt has the potential to form the barrier. We could use the ratio that we created here, for example, as something for the pre-qualification of salt. So from the information gathered in the pre-qualification, in the case of shales, we could identify, as I said before, the shales with the same properties in other fields here in that have the same type of formation and mechanical properties. We can plan the execution of bond logs in some wells uh, in the abandonment campaign when we talking about mature fields. We could, with positive evidence of bonding, we could, in order to qualify the formation, we should be performing both a bond log and a pressure test in the annulus, so we can make sure that be sure that the response in the bond log really has a good response for for a barrier. I mean, when we talk about the pressure that we expect the end of the life cycle of a well, and we should perform the bond log and the pressure test in a certain number of wells that the operator should be defining in order to understand that that formation is qualified. So the qualifying process here would be understanding, correlating actually the bond log response to the pressure test response, and see and making sure that the bond log response is enough, uh, uh, so we for the formation to be defined as an element of a well barrier in a well. This would be the mainly the philosophy of the qualifying process here. We should also keep record of the formations that we qualified. We should be keeping record of log responses, mechanical properties, geomechanical properties, and everything, so we can make correlations into to other formations, obviously in other different fields. And after we qualified a certain formation, it could be salt or it could be the shale, we understand that either a bond log or a pressure test by themselves could be used to verify the creeping formation as a barrier. So we would need both. After we qualify a formation, we can only perform a bond log, and if it brings a good response, we know from the qualification process that the pressure test probably is going to be good. So we understand that this would be enough, and in that part here is when we start saving money in well abandonment campaigns. So this is the main objective of the qualification process here. So I'm also bringing some highlights on the guidelines that we have around the world. We have we use generally the Brazilian guideline, but we know that we have a guideline in UK, and we have also a guideline in Norway. And we see some differences here that of understanding. So in in the first line here, we see accepted length for cement as a barrier. So we use in Brazil, we understand that if we can verify the cement by bond log, a 30-meter MD length would be enough. But if we use a calculation only by the, the cement job parameters, the displacement calculation, we should be needing a higher length for the cement. UK only mentions 100 feet, in Norway, they for a verified bond log is the same as in Brazil, 30 meters, but for the displacement calculation they accept 50 meters. Uh, Regarding creeping formations, actually, the 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 minimum length would be 30 meters here, and it's the same in our SOC. In UK, they just say that the length should be adequate to prevent flow, but they don't actually they don't give us a number. So this is something that the operator probably should prove that the length that it has in the annulus is enough to prevent flow. This could be done by pressure testing the annulus. This is an example. As for the method of verification for the formation, for non-qualified formation, the three guidelines here, they say that we need a bond log and a pressure test. And for, I'm sorry here, it's qualified formation. For qualified formation, either a bond log or a pressure test would be enough to verify the element. And as for the minimum number of wells, the Brazilian guidelines, they say that the operator should define this number, so it's open for the operator to define and to evaluate the number of bond logs and pressure tests that they need to qualify this formation. UK says we need sufficient field experience, so it's open. Uh, Probably the operator should define when it has the sufficient field of experience. And Norway don't have any comments about the minimum number of wells. They just say that formation need to be qualified, but they don't say nothing about number of wells. So this is a bit of a comparison of three references that we use here in Petrobras to analyze this type of formations. So we can see that the regulators here, they already are accepting this. Some regulators actually are already accepting the creeping formations as a well barrier. So this is not something new. This is something that's already been done in some cases. So for just to end the presentation here, I'm showing some future developments. Uh, some of the cases here are applied for Petrobras, not maybe not for some other operators. So as I said, the lab tests that we did, the diffraction, X-ray diffraction, the geochemical analysis, they were all performed in cutting samples, but we could not have a mechanical rock mechanics test because we could not regenerate a core sample from the cuttings. So it's important that we could try coring a rock to perform rock mechanics tests if we understand that we are going to use this methodology in the future. So from the rock mechanic test, like we did in SOT, we should be generating a constitutive model to use in finite element models. And this the shale behavior is not so is not so predictable as salt behavior. So salt, if we have halite, we know the behavior of halite, and it probably halite from Brazil or halite from anywhere in the world, they would behave the same. It depends obviously on the some contaminants that we may have, but generally, if we have 100% halite, it would behave the same. But shales, we could have many different properties for shales, so we should be doing rock mechanics tests for each case. Obviously, we could see similarities by the geomechanical properties, by for the also from the rock mechanics test, but we should be analyzing shales for each case as a different rock. So core sample could also be used to characterize rock fluid interaction. I didn't say anything about this, but this is something that we could use to accelerate the shale creep in the field. So as I said in the beginning of the presentation, the for drilling purposes, it's sometimes it can bring some challenges on well construction, but for well abandonment, maybe after we finish running the casing, we could put a fluid in the annulus that would have a rock fluid interaction, and it could accelerate the creep behavior of the shale, and accelerate the time between well construction and the contact of that shale with the casing. So this is something that we could study in the future. And still in Brazilian scenario, we still didn't qualify any formation. So this is something that we have other technologies that compete with the creeping formation. So in our case, we still didn't see any case that we needed to use the creeping formation, but this is something that we maybe in the future we could be doing. So a mechanistic model for salt creep is developed. We have in the literature here we see different models from the double creep double mechanism, but we still need to qualify in Brazilian scenario. We still need to qualify the salt with logging in the pressure test. So I guess I'm open, Pierre and Susan. I'm open for questions now. I hope I could reach your expectations here with this presentation. Thank you very much for the opportunity.
No, no, absolutely. Thank you. Thank you, Fabio. We've had a number of questions from the audience already, and maybe we're going to take those first. I'll show one from Basker Murugapan. It's about explaining the various stages of creep, what happened exactly in stages 1, 2, and 3, and whether those would be related to other phenomena that are um, already kind of known when built, constructing wells, like the leak-off test, for instance.
Okay. When we talk about the times in the related to the drilling, probably the salt would be reaching stage 2. So it probably we would have the initial closure as a primary creep in the salt. It happens very fast, and during the times that we have to drill the salt section, at least in pre-salt scenarios here, we would probably be reaching the second stage. Uh, this is a very good question. Like how this creep behavior would influence the maybe the interpretation of LOTs. So this is something that we are working on in Petrobras. We have a project with an university here in Petrobras, and we are studying just this type of behavior. So how the deformation of the salt could influence the interpretation of an LOT. I mean, when we have uh, a linear behavior, and when the pressure it leaves it becomes non-linear. So how is that really a leak off, or it's a salt deforming? So this is something that we are studying right now. So this is a very good question.
And the second
Uh,
question from Basker was in
yeah,
non-elastic behavior, does it actually leak to loss of seal integrity?
yeah, we have performed a lot of microfractures, microfrac tests. So extended leak off, and we see the behavior of we do have a generation of a fracture. So this is something that really happens, and we can also see the this behavior during cement jobs, for example. So we generally set the casing in the top of salt, and we drill the whole salt section, and we perform a cement job in a production casing. In some cases, we have loss of circulation, and we don't have any changes in the top of cement that we expect. So we understand that the loss of circulation would be in the previous casing shoe, that is set in salt. So this is something that really happens. Yes.
Very good. And we're going to take a question from Alex Algora. It's about casing collapse.
Mm-hmm.
If the salt creeps in so quick, just a few years, wouldn't that pose a higher risk of casing collapse during well's life cycle? This is something that we should be considering in a casing design. Yes. So after we during the construction, this is not an issue. But when we talk about life cycle, as he's saying here, like 20, 25 years, we should be evaluating that. But the behavior that we expect in general is in the base of salt, we have the salt would creep in, and maybe in the top of salt section, depending actually on the length of the salt that's exposed in this annulus, we could have the salt being like opening. So creep in the lower part of the salt section and creep out in the higher part, in the upper part. So this is something that could happen, and but we understand that probably during the life cycle we would have an increase in the pressure in this annulus due to the changes in temperature. I mean, the well is producing, sometimes the well stops, sometimes we have an acid job, sometimes we in order to restart the well, we need to do a bullheading, and we inject a cold fluid. So the changes in temperature in well, they would change also the pressure in the annulus in the salt, and it's the salt creeping in also increase the pressure, and the we expect a fracture in the generally in the top of salt. So the fracture would perform as a like a fail-safe device. So we are generally we need to know the fracture pressure here, the fracture gradient, and we consider that fracture gradient as a limit for our casing design. So this is something that we need to consider. It was a
I'm
very
going to
good
jump in
question.
really quickly because for clarification. So you mentioned temperature as being a main factor, but I would think that flow rate would be the biggest protection against
Yeah.
deformation of the pipe, because once you keep a certain level of flow, you're going to have the pressure pushing out against the pipe. And then, as you mentioned, if you're having to re-enter and do something and change um, shut in the well for any reason, that's where you'd have some issues.
The flow rate of the production, or the flow rate during the drilling?
The production.
The production, yeah. Yeah,
Yeah.
the flow rate during production would maybe accelerate the temperature changes. And we also have ballooning effects in different cases. This ballooning effect,
Yes.
it also can increase the pressure in the annulus exposed to the salt. So this also all of this should be considered in a finite element model. So it's a very complex thing to model. We are actually working in in this modeling right now in Petrobras. We have some sensors that we put in the salt annulus. We were able to put this I mean, in some wells here in our case, and we are still interpreting the pressure data, and still running models to see if we can match the information from models with the readings that we have from those sensors. So this is a very complex thing to model, yeah. But it's something that an operator should be considering for casing design.
Yes, definitely. Well, we have lots of questions.
So we have lots of questions. If I can slot in one of mine, you've talked about bringing cuttings to surface and taking cores in salt, for instance, or in shale. Um,
It
how,
was in shale, yeah.
yeah, how easy would it be for you to then work on deep core shale that you would then bring back to surface, and about the stress relaxation, and how good would that be a material for you to work on? Any limitations there?
Okay, so yeah. For what I know, we need to be very careful when we core shales. We need to like we need to freeze the cores. We need to avoid contact with water because it could actually I mean it could contaminate the sample. We need to put those samples inside oil so we can avoid contact with humidity from the air. So it's very challenging to core shales. We don't do that a lot here, but if we if we if we intend to use that type of formation as creepy for well barriers, we should be doing that. We have experience with core sampling of shales, but this is something that really could impact the analysis, mainly the mechanical behavior. I mean, it could be really if we don't have any we don't have the if we don't take care of the core from the drilling rig to the lab, it's probably going to influence the behavior. For
Yeah.
geochemists, for geochemical analysis, I mean, it would not be an issue because we are only thinking about the composition and everything. But for the mechanical rock mechanics test, yeah, this is really an issue.
And if this is an area of research that is quickly progressing, then you're faced with the issue of preserving the cuttings that you have today for tests that might only become available
Yeah,
tomorrow. So I don't
we
know how
we
you address
I
that.
don't know if we had this type of care with the cuttings. So uh, that's also actually why we couldn't perform any mechanical tests in the cuttings. Only composition. So geochemistry, composition. This is something that if the cuttings are, I mean, swelled with water, it wouldn't be an issue. But for mechanical behavior, yeah, we cannot use that.
Yeah,
Yeah,
swollen or dry.
I know that we have some researches on reconstructing, maybe resedimenting shales from cuttings or trying reconstruct rock, mixing the cuttings with cement. But this is something that I don't know if we have reliability enough to understand that reconstructed rock represents the rock in the field. So, but this is something that probably we can address in R&D projects here. Yeah.
Good question from David Baldwin, and it's about type rock typing for clay, trying to see if you could have a an activation fluid.
To understand type of.
Yeah, I think that's a really
Yeah,
good
we
use, the
this
clay mineralogy. But just to jump in, is from a geological perspective, every clay behaves differently,
yeah.
has different properties.
That's why we should be qualifying the different type of, we cannot use the process for a certain type of shale to other ones. So shale is they have a very different, if it depends on the clay content, the type of clay, I mean smectite or not. This is something that will probably, yeah, but we don't have any work on this activation. This is something that I put in the future potential, yeah. So this is
For,
something that we should be pursuing for the future if we want to, if we
and
have the strategy of using that. Yeah.
I'll add one curious question of mine. Then you've talked about the seismic attributes and the shale beds that can be mapped. Do you think they will have the same properties within the same shale bed, or do you think there could be some significant mechanical or chemical
Uh,
properties
this
within that
this
same
is
bed?
something that we could, I mean, we could use that as long as cuttings to see if they have similar behavior, but probably in a qualification process, if we have any doubts about that, we could took some well in, I mean, spaced in geographically spaced in the field, so we could see if really if the expected behavior that we have for that shale is really happening. So probably this would be part of the qualification process. So that would influence the minimum number of wells. I mean, the homogeneity of the formation laterally is something that we should be worried about in the qualification process, for sure. Very good question. Yeah.
I 100% agree with that.
Yeah.
I'm going to show one by Maria Eugenia about micro channeling in case of gas migration. When you have seen sustained casing pressure, abnormal casing pressure in wells, have you looked at the potential of shale to have formed a barrier? And then the other question, which is, okay, what about partial cementation? If it's clear that the casing is uncemented, then that's one case. If you think you might have some cement and some of the formations will be squeezing, how do you manage that case?
Let me try understanding the question here. Each method. It, yeah, if we have micro channeling in a maybe in a if I understand correctly, in a cement, probably we would need to re-cement the part. So the main tool that we use would be the PWC, perforate, wash, and cement, to correct the cement. And we still don't have any, as I said before, we don't have any qualified information, so we never use that. But if we were expecting the formation to avoid the gas migration, we would need to perform a pressure test and see if it really holds the pressure that we expect. But I don't have an example of use that in Petrobras. Yeah.
Okay, and we'll take one question from Siri Karn, and she's mentioning smectite and the role of smectite in the behavior. Any comments on that?
Yeah. The presence of smectite is probably one of the things that we would be seeking in a shale. But we need to really see that the swelling of a shale and the creep behavior, these are different things. So the swelling, because of the smectite, it happens it happens in the very small particles of the that form the shale. I mean, and the creep behavior is a mechanical behavior that's from the shale as a whole. So the maybe if we have a swelling, I don't know if this shale that swelled would have the same mechanical properties as the shale that creeped in the well. So, but this is something that probably enhances the ability of the shale to creep. But we need to see if the mechanical properties of the shale that suffered the swelling is enough to form a barrier. And this would be done with the bond log along with the pressure test. Yeah.
I think also if you look at the crystal structure of clay minerals, they are elongated and they can create almost like a glide plane versus halite, which is cubical, and so it's going to have different behaviors um, under different geomechanical conditions.
Yeah. And also the behavior of the smectite content, this behavior depends on the type of drilling fluid that we are using. If it's a water-based mud, there's a behavior. And if it's a oil-based mud, maybe we wouldn't have any type of swelling. So this it depends on the drilling fluid, that drilling mud that we are using during drilling. Yeah.
But like you said, over time, that kind of doesn't matter as much as the differentials of pressure and the geomechanical issues of having the annulus against shale that is being as under pressure and creeping.
Yeah.
We'll take one last question before we have to close. But question from David about the pressure test of the annulus and the test of the annulus that you have mentioned during your presentation, Fabio. What method did you use to validate the integrity of an annulus?
Yeah, we could perform a formation integrity test. We could perform a leak off. I mean, I think the most critical part here would be this that David mentioned, the maximum expected reservoir pressure. We need to make sure that the formation withstands this maximum pressure. So if you perform an FIT, I mean, a formation integrity test, in this maximum pressure and the formation holds, I think it's okay. We could
Uh,
also perform a leak off to a higher pressure to see the limit that the rock
well,
withstands, or we could also perform a micro, I mean, extended leak off. But we need to just to guarantee that this maximum expected reservoir pressure is uh, would not break the rock.
right,
So it's
but
similar to
from a
formation tests, I think. Yeah.
Yes, but from a purely a practical standpoint, Fabio, I'm not sure that's what David meant, but
Okay.
because formation tests are usually carried out with the lower section of the hole open when an annulus test is conducted from above. So sometimes you will have more formations open and you will have formations with a potentially weaker properties than the one you want to test, right? So unless that section is very short and you've isolated the shale you want to test, doing an annulus test in practice might present some challenges. Yep.
In maybe in this test we should be performing a perforation in two different
Yep.
parts. So
Yep.
we do a
Yep.
perforation below. We isolate this part, and we
Yep.
have a perforation above. And if we see leakage in this between those perforations, we would see the flow in the
Yep.
perforation below. So that would be the way that we perform those tests.
I think you've
So we
answered
could
the
avoid
question. Yeah.
the yeah. So we could avoid the false interpretation maybe if we have a leak off in a formation above. Yes.
Wakas is joining us. Any questions or curiosity from your side, Wakas, before we conclude?
It's a great topic that was covered. Thanks a lot, Fabio, and all the people who joined us through various platforms. Thanks a lot for joining. It was a truly engaging session. And please follow us on the LinkedIn. We have more exciting topics coming up with well integrity. And I will let Susan and P talk more about it. Follow us on the LinkedIn. We have some interesting topic coming for the rest of this year. Thanks a lot.
Very good. So there'll be. I'm showing the next poster for the next event. We had some questions. Some of them were being answered by Alex Lucas, who will be the host with Susan of the next webinar. And at this stage, I'd like to thank everyone for joining today, Fabio in particular for presenting, and the audience for Q&A and comments. And we hope to see you again. We'll now conclude with a short video from SB. See you
Thank you
later.
very much, Pierre,
Thank you.
Susan. Thank you for
Bye
this opportunity. Yeah.
bye.
You know, people ask me why they should join SPE, and what I tell them is that SPE is absolutely essential. Frankly, if SPE didn't exist, somebody would have to go out and create it. When you graduate with a technical degree, a petroleum engineering degree, or other engineering degree, you get a lot of really good knowledge that gets you started on your career, and you learn a lot on the job. But the jobs that we have in this industry, they're really quite difficult. And you've got to have other resources, either to solve specific problems you might be having at the moment, or to better understand how to solve, daily issues that you work on. SPE provides opportunities to learn about new things that people are working on. There are great articles in JPT Magazine and the other magazines that we have that are really useful. If you're not reading JPT every month, I tell you it's essential to do that to keep up with the technology. We have excellent conferences where you can learn from people who have solved very difficult problems in our industry. And doing that is just incredibly important and incredibly useful. To me, I don't see how you can be an engineer working in the petroleum industry and not find value in the resources and the opportunities that SPE provides. It's an opportunity to meet people who can help you in the industry, and it's an opportunity to get the knowledge you need to be successful.